All right, hi, I'm Shuai. I work at Stony Brook. The work I'm going to present is DepFast, orchestrating code for quorum systems. What's special about this work is that we're focusing on not algorithms, not designs, but we're trying to write better code that is easier to manage and follow. Okay, so what is a quorum system? A quorum system has a foundational communication pattern where we have a node broadcast requests to a group of nodes and then collect responses. The system will then proceed with a quorum. The quorum size can differ. For example, it could be a majority, a supermajority, or all of the nodes in the group. A typical example of quorum system is consensus systems based on consensus protocols such as Epexus and Raft. So quorum systems are widely used in practice, especially in fault-tolerant systems, such as coordination services, databases, and blockchain systems. Quorum systems are hard. They have very complex state transitions. For example, we have a node broadcast requests and wait for replies within a timeout. There are lots of conditions we need to process. For one, we could receive majority yes replies before timeout, or we can receive a majority of no replies before timeout, or at timeout, we could receive a majority replies, but they are a mix of yes and no. Or at timeout, we could receive not enough replies. And there's more. In advanced quorum systems, things could be more complex, mainly because we need to process multiple different sized quorums in a single broadcast. So, for example, in addition to the 4 conditions we talked about, we could be waiting for a super majority of yes replies before a second timeout. Or before the second timeout, we could receive enough no replies so that a super majority of yes replies is no longer possible. Or at the second timeout, we could receive not enough replies to form a supermajority. So coding all these complex conditions is a very hard job. And the question we try to ask and answer today is, how can we make the code of these systems easier to write and follow? Well, first let's look at the status quo. What's our current way of writing the code for these systems? The way we often use is asynchronous coding style or event-driven. So we write the broadcast in one function, and then we have another function to handle the reply messages from that broadcast. So this reply message handler is usually triggered by a message loop that keeps looping over incoming messages and dispatch the message to the right message handler, okay? So why do we write code like this? Mainly for 2 reasons. One, we have been educated for many years that this is the right way to write fast network programs. And there are many famous open source libraries, such as libev, promoting this style. And number 2, coding this style is consistent with some pseudocode or some types of formal specifications, such as TLA+. However, coding this style has issues, one of which is known for many years as stack ripping. Basically, we're breaking the continuous logic into 2 separate functions. And this means that we have to manually manage the context shared by these 2 functions. For example, in this case, we have to properly manage the entry variable. And more. The callback function is not triggered only once, but triggered multiple times. And as we develop the systems, we write more and more callback functions, which eventually cause too much cognitive load for the developers. This is also known as the callback hell issue. So how can we address these issues? Well, this brings us to the eternal debate of asynchronous coding versus synchronous coding, or event versus thread. So here is a typical example of asynchronous code or event-driven code where we trigger RPC in one function and we write another handler function to handle the replies. We can convert this asynchronous code to synchronous code using thread. So basically calling the RPC will block the thread. Well, coding this style is much easier to write and follow, but it is potentially much slower than the event-driven code because of the overhead of using threads. And in the past many years, people have been using lightweight threads, such as fibers or stackful coroutines, to mitigate this effect. And actually, it's proven that using lightweight threads has very low performance overhead, and is almost as fast as event-driven code. And this inspires us too. So we built this framework called DepFast, which is a coroutine-based framework. So it works as a user space library that a process can link to. We provide this stackful coroutine interface, so users can define their own tasking. We also provide common utility functions such as RPC and coroutine scheduling. We did spend a lot of time building these features to help us build distributed systems easier. But today, what I want to show you the most is the event abstraction that we come up with to help us develop quorum systems. So I want to show you this interface, coroutine interface, with the same broadcasting example. Here is how we create a coroutine. And here is how we do a broadcast, basically by triggering RPC to each server. And this RPC is non-blocking. It returns an event object, RPC event. In our namespace, we call this event, but conceptually, it is similar to a condition or a promise, if you're familiar with those names. And then we can wait on the RPC event to collect responses. So here, you might spot a problem already that we're doing this wait sequentially. So each wait will block the coroutine. So it kills all the concurrency of out-of-order replies. So it will have low performance. It is also difficult to express the complex conditions, such as a collective timeout on all the RPC events. So this is why we invent the QuorumEvent abstraction. So a quorum event is a collection of events. So here, we add the RPC event to a quorum event. And then instead of waiting on the individual RPC events, we do a collective wait on the quorum event for majority. And the library in the background will guarantee concurrency. It will process the replies out of order and unblock the wait as long as a majority of yes replies achieved. Also, it makes expressing complex conditions much easier. We can just go through the conditions with a simple if-else statement. So it would be much easier to express conditions such as reject or timeout. Okay. Next, I want to show you the expressiveness of DepFast using a real example, Epexus. So Epexus is an advanced consensus protocol that has a fast path and a slow path. So in the broadcast, if we receive a supermajority of yes, we go fast path. If we only receive a majority yes, we go slow path. Epexus is a very popular project. It's well liked by the community, including us. Not only its design, but its code is widely used in related areas. Okay? So how can we expressively implement Epexus? First, let's try to draw the control flow of Epexus in a human-friendly way. First, we have a broadcast, and then we wait for the conditions for fast path. If it succeeds, we go fast path. Otherwise, if it doesn't, we try to wait for conditions for slow path. If that succeeds, we go slow path. Otherwise, we go error handling. So now I want to imagine how can we implement this using asynchronous style, event-driven style coding. So what are the events? We need to process at least 3 types of events. First, we need to process the reply for that broadcast. And second, we need to process the timeout for the fast path conditions. And third, we need to process the timeout for the slow path conditions. Okay? So all these 3 types of events, and they will actually form very complex, non-deterministic state transitions like this, which will further satisfy or deny the conditions in the main control flow and out of order. You can imagine this will be very hard code to write. So how can we write code in DepFast for this? Okay. In DepFast, we do broadcast and initialize the quorum events. And then we wait for the fast path conditions. And then if it succeeds, we go fast path. Otherwise, if it fails or timeouts, we try to wait for the conditions for slow path. And then if that succeeds, we go slow path. Otherwise, we go error handling. As you can see, this is very human-friendly code, right? It is almost direct translation of the main control flow. Makes things much easier. Well, you may wonder, okay, this all is natural. So what's it like to write Epexus without DepFast? All right, this is the code we copy from Epexus' original code repo with some simplifications. This is the message handler function for the broadcast. Well, first probably you may notice that with this coding style, we often have to mix the main control flow with some minor case conditions, such as this is handling a delayed message. We have to do early return. Right? This makes our code a little bit untidy. Next, you may notice that there are 2 to-dos in this code. These are actual to-dos in Epexus code. And if you want to implement these to-dos yourself, you'll find that it is harder than I thought. So for the first to-do, when you receive enough rejects, okay, what you need to do is you need to invalidate the entire quorum, including you have to invalidate all the future messages. All right? So this cannot be a local change. You cannot write 3 lines of code here or make a function call here to implement this. You have to rewrite the entire function. Right? Second to do is similar. It is processing timeout. Right? We know that processing timeout in an event-driven style is very difficult. You at least need another function call for this. And we know some nice hacks from later projects based on Epexus is that you can trigger an empty message at timeout, right? So that's a nice hack, but more and more such hacks in our code, harder and harder for people to follow the code. So the last problem I want to discuss is this. So you may notice that in this code, the fast path quorum and the slow path quorum, the sizes are the same. They are both a majority. Okay? This is actually a special case for Epexus. They have optimizations that when the replication group size is 5, the size for both quorums is 3. So they can write code conveniently like this. However, if you want to support more general case, like replication group size more than 5, you cannot write code like this. You cannot replace one of the number with a larger number. It will cause liveness issues. So if we look at the the DepFast version code again, we don't have these issues. Okay, next I want to talk about another example, Copilot. This is not GitHub's Copilot, but a consensus protocol published in 2020, which has a nice feature that tolerates any server fail slow. Okay, it also has a fast path and slow path structure. Copilot's code is based on Epexus code, and it has about 2,500 lines of code. And we re-implemented Copilot with DepFast. So with all major features implemented, our version is about 1,600 lines of code in C++. Here, I want to show you a comparison of the algorithm and DepFast version code and the original Copilot code. So this algorithm description is we directly copy and paste the text from the paper. Again, first step, do a broadcast. The second step, gather the fastpath quorum, wait for the fastpath conditions. And the third step is go fastpath if it is satisfied. And fourth step is if fastpath is rejected or timeouts, go slow path. Okay. All right. So without looking too deep in the code, I think we can already notice that DepFast version is cleaner, right? It's easier to understand. It's an almost direct translation of the text. And it handles complex conditions such as timeout more elegantly. Well, another problem I want to discuss is, very interestingly, this is exactly the problem we chatted earlier, that for Copilot, the fast path quorum size and the slow path quorum size are no longer the same. They're different, which means they cannot directly reuse Epexus code for this. So eventually they come up with a nice hack that they reversed processing the slow path and fast path so that it avoids the liveness issue. It's a nice hack. Again, it's a nice hack, but more and more hacks we have in this code, it's harder for us to understand it. Okay. Next, I want to show you evaluation comparing our Copilot implementation against the original Copilot implementation. So we'll try to answer two questions. One is about performance. Like, do we have a lot of overhead compared to the original implementation? And we did this test on Azure with a 3-replica setup. The second question we try to answer is, can DepFast help developers to deal with complex cases, such as fail slow? So we measured this did a fail slow test, in which we injected different types of fail slow errors, such as on CPU, network, and the memory. So this is the results for the performance test. The x-axis represents throughput, and y-axis is the median latency. You can see that DepFast version of Copilot has about similar performance compared to the original implementation with a slightly higher latency. So the next question, fail slow. So this shows the fail slow test, and each figure, the blue bar represents the case where there are no failures, so it serves as a baseline. And each other color type represents a different type of injected fail slow failure. And the expectation is the throughput could drop, but no major drop, not like less than 20% or so. I do want to say that we verified Copilot in its original paper's setup that it can tolerate any server slowdown. However, in our own tests, which are different from original Copilot's test, that we noticed something interesting, that in some cases, the original Copilot implementation has more throughput drop than we expected. And in one case, it crashed. In comparison, DepFast version has no such issues. So I do want to emphasize that we're not trying to bash the Copilot's implementation. It is an academic prototype which has done its purpose well of validating the idea. The message we're trying to communicate here is fault tolerance is not only an algorithm issue, it's also an implementation issue. Okay, quickly summarize my talk today. Quorum systems are very hard to build, and asynchronous programming style makes it even harder. So we present DepFast with a QuorumEvent abstraction to make things easier. And we analyzed 2 cases, Epexus and Copilot. You're welcome to check our paper, which has more details on the internal designs and more results of the Copilot evaluation. And it has a Raft implementation. Also has more discussions on slow failures. Thank you. I'm ready to take questions.